All right, so far we've went over the practice of testing hypotheses and kind of theoretically how it works. Next, I want to talk about uh, how hypothesis testing works in practice and some of the limitations of hypothesis testing, especially some of the limitations of relying on p-values. So there are some important limitations to p-values. They're used all the time. They might be the single most used things in statistics across almost any part of science. But one thing is that these decisions that are made about whether you believe that the null hypothesis is supported and should be retained, or if it should be rejected and you should take up the alternative hypothesis, that's only one decision or another. In reality, um, the evidence is often a little bit more vague, and it's somewhere in between. So one of the issues with it is that you have to decide on that cutoff point when you're doing hypothesis testing. So in this case, if you get a p-value of 0.049, that would suggest that the hypothesis is supported. You would reject the null hypothesis. If you have a p-value of 0.051, you would say that you retain the null hypothesis, that there was not any support for the alternative hypothesis, that there is some sort of difference. So you look at this and you'd say, you're making very big differences in your decisions just based on, 0.002 difference in probability. One of these, if the null hypothesis was true, would occur by chance. That extreme, 5.1% of the time, other ones up to 4.9. If you run the exact same study in the exact same sampling frame, like run a sample of 50 participants at Wesleyan and another 50 participants at Wesleyan, you're going to find this much of a difference a lot of the time. So these p-values can dance around a lot, but you can be making very different decisions based on the specific p-value. And so with that, I would say that you want to be careful not to read too much into an individual study's p-value because, again, this can change around a lot, and very small differences in the decisions that you make in a study can really impact whether it goes above or below that cutoff point. Another limitation to relying completely on those p-values is this is basically the idea that if the null hypothesis were correct, you'd only get values that extreme 5% of the time, which seems like, pretty good. 95% of the time, if there's nothing going on, you wouldn't find anything. So that seems pretty safe. But let's say that we have a really strong opinion that jelly beans cause acne, like in this XKCD comic. So we might be looking at this and say, we are convinced that jelly beans are the scourge of everyone's complexion and they cause acne. And so we're going to go about testing that hypothesis that jelly beans cause acne. So we go through, we run one test, and we use purple jelly beans the first time because, it could be all different colors of jelly beans. And we don't find anything. And then we do this with 20 different colors of jelly beans. And, just by random chance, we have that result that green jelly beans were associated with having acne. And then it gets written up in the news as green jelly beans are linked to acne. And this is something that would only occur by chance 5% of the time. So this is a statistically significant result. This is very exciting. Maybe someone is going to, go on a talk show and talk about how bad green jelly beans are for you. Maybe someone's going to write a book about why green jelly beans cause acne. But, if we run basically the same study over and over again 20 times, on average, we're going to get a p less than 0.05 1 out of those 20 times, if you do the math. So Essentially, if there's a lot of people running a lot of the same types of studies over and over again, or if there's a lab that's trying to find a study and they're trying, a whole bunch of different versions of the experiment over and over again, you can find that you're eventually going to get some promising looking p-values. And so because of this, you want to be transparent about how you're testing hypotheses. That is, if you are running multiple versions of a study, you want to inform the reader that you maybe ran one experiment and the p-value was greater than 0.05, and then you ran another one and it was greater than 0.05, and then you ran a third study and you found support for the hypothesis in that final one. If you're being transparent, then people know how to interpret those results. Maybe you're not going to be quite as confident. So that's one thing, is that transparency is very important. Another thing that you might want to take into account is that you can try to replicate the study. So with that, if you try it out a few different ways and you find a result, you can run exactly the same study, exactly the same criteria, exactly the same materials again, and then see if you're able to find those results again in a second sample. And if you don't, maybe again, this is just a random chance thing. So one big takeaway from this is that with hypothesis testing, if you're just looking for individual studies to support your hypothesis, it's not that hard to find one study that is looking good for you. But we can be careful about this by looking at results across multiple different studies and also making sure that we're reporting everything that we're doing in those studies. So one thing that we might want to do, in addition to not getting those type 1 errors, is reduce type 2 errors by increasing power. So one thing you can do to increase power, so that is the probability that you would find support for the alternative hypothesis if there is a difference, is to look at studies that have larger effect sizes. So a larger effect size means that there is a bigger difference between the null hypothesis and the observed effect. So for example, if say you had a control condition where you measured levels of anxiety, and you found that in the general population, levels of anxiety should be, say, 3 on 1 to 7 scale. If you had a score of 4, that would be a pretty big effect size. But if you had a score of 6, that would suggest a really large effect size for whatever intervention you did. So we've already talked about correlation coefficients in the past. Remember that a 0 means there's no relation. 1 means they're completely the same thing. And -1 means that they're the opposite of each other. So the further the correlation coefficient is from 0, the stronger the relation between the variable is, and the larger the effect size is. So you have more power to find a larger correlation. So maybe if you know that you won't have a lot of resources and you really want to find something, you might say, oh, I'm going to look at research where I'm likely to find a large effect size. And if I'm not likely to find a large effect size, maybe I don't focus on that. Or if you're thinking about designing an experiment, you might want to think about how you can increase your effect size. If you're studying people's emotional responses to stimuli, you might want to make sure that the experimental condition where you're trying to elicit the emotion strongly elicits that emotion so that you get a larger effect size. So that's not just correlations, that might be differences between frequencies. So if you flip 12 coins, like in our lab example, you get 8 out of 12 heads, that would be 2 more heads than you would expect by chance. So the effect size there would be 2 greater than chance. If you got 10 out of 12 heads, that would be a difference of 4. And so the effect size for the 10 out of 12 condition will be larger than for the 8 out of 12 condition because it is further away from what you would expect by chance based on the null hypothesis. So another thing that you can do is that you can increase the sample size. This is a theme of what we've talked about so far in this class, is that in general, larger sample sizes are better. If you have a study that you're looking at where you're looking at some difference that you don't expect to be very large, but you're very interested in, maybe you need to have thousands of participants. And again, this might be a practical issue where you can only collect as much data as are available during the semester. But this is something to keep in mind, that if you have a small sample, it's going to be very hard to detect any differences unless you have very large effect sizes. So this is about managing your expectations and also planning out your studies so that you account for that. So sometimes when I'm asked about my opinions about a study, the data have already been collected, and maybe there's only data from 25 participants, which would generally be a pretty small sample. And so the only thing I can say at that point is you'd need a really big effect to detect that. I would say either collect more participants or maybe look at things in a different way in that case. Because if your sample size is very small, there's often not much you can do. Again, you can't really do anything magic with statistics. You can only, follow these rules and analyze whether this is more than expected by chance. So, if you have really large effect sizes and you have a big sample size, power is going to be really high. If you have a small effect size and you have a small sample size, you're not going to find results that are supporting rejecting the null hypothesis very much. And so, of course, this can be a problem because it might be the case that there's something that you want to uncover. And in reality, maybe there is this small but important difference out there, but you're not able to detect it because it's hard for you to get a large enough sample size. So this is a practical issue that we run into with hypothesis testing. So one thing that you can do is that you can conduct a power analysis. So ideally, you do this before you collect the data. And so you specify, if we use an alpha of 0.05, if we expect the effect size to be an R of 0.3, for example, and we collect data from 300 participants, what is our power? And then we'd get those results. Maybe we run that analysis and the power is only 0.6 or a 60% chance of finding support for the alternative hypothesis rather than the null hypothesis. That's below that 80% cutoff. And to me, 60% doesn't sound very good. It's barely better than a 50-50 chance of the results working out as expected, assuming that you're actually correct. So in that case, you might look at that and you'll say, okay, do we have enough resources? Maybe we can increase the sample size to 400 or 500 if that's practical. And then you might look at that and say, okay, now we have 90% power, which sounds a lot more promising. So as I said, you ideally want to do this before you run a study. You can also look at what's referred to as a posteriori or observed power, and you can plug in the value that you got and the alpha level and the sample size, and it'll tell you the observed power. But statisticians usually recommend against doing this because it cannot be very informative, because that's telling you what you already found, and you might have found a big effect size, again, just by chance, because this jumps around just like p-values. And so there's sometimes been debates where someone has a very small sample size of, say, like 15 participants, and their argument is that's not a big deal because we found the results. But that's thinking about things in reverse, in that, well, you would only find very large effect sizes with a small sample. And if the effect size actually is small, we shouldn't expect to have these really large effects. So this is something, again, based on your knowledge of the area of research, based on how much resources you have, how easy or hard it is to reach samples. You will have to make practical decisions about how you're running your study. This is basically the way that you go about null hypothesis significance testing. You're basically getting this observed value, so the mean level difference between two groups, or the correlation coefficient, or other types of test statistics we'll talk about later. And essentially what you're doing is you're making rules about this is the cutoff point for when we're going to conclude that this is something that would be unlikely to happen just by chance. And then we're saying, okay, hypothesis appears to be supported. So this has become very common in science because it allows us to make some decisions to make some sense of the data. So we're not saying, this is definitely right or this is definitely wrong, but, just based on the results of this individual study, you can be making decisions about whether you should believe an intervention is effective or it isn't, or whether you believe that a personality trait is associated with the behavior or isn't associated with the behavior. And with this, you're also being a little bit conservative about whether you're making claims or not, in that unless you have results that are unlikely to occur just by chance, you assume the null hypothesis. That is, our standard is we don't basically assume there's any good evidence for something unless we get beyond a certain cutoff point where we start saying, okay, this is statistically significant. We think that there is something going on here. Of course, it's also very important to avoid getting trapped by p-values. And so sometimes when we're running studies very quickly, we can get into the habit of just looking quickly for a specific p-value. Just maybe we run a whole bunch of things and we all have this whole page of results and we're going through quickly. It's like, okay, that p-value, those are the things that are supported. And then we write up, all of these things are supported, all of these aren't. So again, you want to be looking at more than just the p-value. And again, being kind of humble about how much the results are supported, because even though null hypothesis significance testing is valuable and having those p-values is valuable for making those decisions, this can change a lot from study to study and can end up being overinterpreted. So you've probably seen examples in the media where there's some individual study that was ran and they found results that supported the hypothesis, and now they put out information that, standing in this specific way works really well to increase your confidence. Everyone should start doing this. And then more people run the same study and it actually doesn't work out. And it ends up being, maybe we should have been a little bit more cautious before making those conclusions. So one thing is that p-values and anything in statistics does not prove anything. It doesn't prove that you're right. It doesn't prove that you're wrong. It doesn't establish facts, whether things are true or false or anything to that extent. Again, this is all an application of using basic probability theory and looking at our results and saying, if there was really no difference, what % of the time will we get this extreme of results? And so individual studies and even a whole bunch of studies never really prove one thing either way. There's always the chance that we're making either a type 1 error or we're making a type 2 error. And you should be looking at all the available data. So within your study, you look at the p-value, but also look at your effect size. You'll want to look at whether your statistical assumptions are met. You'll want to look at whether your sample is representative or not. And if it's not, you might want to collect another sample that is more representative or has a different type of sample. And so again, you are going to want to make sure that you're careful before making big claims about anything. All right, and so with that, we'll jump into the example of talking to Raja about how we can design that study to test whether or not he eats more food when I'm not at home than when I am at home. Now let's talk about how we would go about testing that hypothesis having to do with Raja eating his food. So let's start with the research hypothesis. So our research hypothesis is that Raja doesn't like eating food when he's alone. He prefers, Raja likes to eat food when he's alone. He prefers to eat food when I've left for work, so he feels weird eating food when I'm here. So that would be a bit hard to test statistically, so we're going to make that a statistical hypothesis. So our hypothesis is that Raja will eat more of his food when I'm not here than when I am here. So let's break it down into 1 hour increments, and we maybe flip it around that between 10 and 11 a.m. every day, I'm either here or I'm away. And then from 3 to 4 p.m. every day, I'm either here or away. And I might look and measure it such that I measure how much food he eats each time after each of those hours. So I'm comparing, and so then when we're doing that, we'd be able to create a null hypothesis and an alternative hypothesis. Oh, you hear something outside of the door, don't you, Raja? Yeah. And so the null hypothesis would be that Raja will eat exactly the same amount of food when I'm here and when I'm not here. So if I measured it at the end, there shouldn't be a statistically significant difference. Alternative hypothesis would be that Raja will eat more food when I'm not here than when I am here. So maybe I measure the amount of food he eats each time, and I find that there's more food that's eaten when I'm not here. So if I'm doing that, I could, by chance, find that there is a difference in my sample. Say if I collect this data on 30 different days, but in reality, Raja doesn't care, and he's going to eat the same amount whether or not I'm here. That would be a type 1 error. Or maybe there is an effect, that is, Raja does eat better when I'm not here, but just by chance, there wasn't a statistically significant difference. That would be a type 2 error. And so when I'm looking at that, I could choose the significance level. Maybe I do alpha 0.05 because that's the standard that we use. And for power, we might want to look at that and figure out how long I should be collecting data. So with that, maybe we do a power analysis. And I'd say, okay, I would expect that Raja eats, say, 50 more grams of food every day. That might be the effect size that I put in. And then based on that, I might want to look and see, how many days do I need to collect data if I expect him to eat 50 grams of food. So I'd want to see how much variability there is over different days. So maybe he, on average, eats 200 grams of food. Sounds about right because he's so tiny. And the standard deviation of that might be 50. So then that would give me a sense of the sampling distribution. And then based on that, I could start doing a power analysis and say, okay, based on that, I'm going to have to collect data for 100 days to figure it out. And I might look at that and say, okay, that makes sense, that's practical. Or I might say, I need to figure this out quicker. If I have to wait 100 days to see if what I'm doing works to make him eat food, he might be really skinny by that time. So this might be something practical in terms of how long we collect data. Right, and then at the end, I would be looking and getting a p-value for how much Raja eats food, whether I'm here or not. And if that p-value is less than 0.05, and the effect is in the direction that Raja is eating more food when I'm not here than when I am here, then I would be able to conclude, yes, Raja appears to eat more when he's alone than when he's not alone. And I can use that and say, okay, I'll put out his food every day. and I'll go for a walk and I'll come back and he'll eat his food, and I can be confident that that then works. So that's just kind of a silly example of how that works. But in practice, this is how all hypothesis testing is going to work. So if you're doing an honors thesis, for example, and you're using quantitative data, you'd want to specify ahead of time. Maybe you're interested in whether or not putting up posters about recycling makes students recycle more. And then you might have a control and an experimental condition that you compare, and you'd have to figure out some of those things. How many people would we have to give a survey to? How long would that take? What effect size would we maybe expect there to be? And then how can we analyze whether or not we think that our intervention to increase recycling worked? So this is something that we'll be going through the process of doing, basically with different types of data. And so for the next thing I'll be talking about in your next section, we'll be doing analyses with categorical data, and I'll be introducing you to chi-squared analyses.